For today's webinar, we have Dr. Peter Stout from the Houston Forensic Science Center presenting Mapping Technologies for Crime Scenes. Without further delay, here's Dr. Stout.
Hey everybody, I was going to talk today a little bit about mapping technologies for crime scene and use in crime scene. So small caveat, I am a toxicologist by training, not a crime scene investigator. This is all stuff that really is done by the folks in my crime scene unit. We are in the process of validating a lot of these technologies. We haven't really put them completely into actual casework yet, but you can see the advantages of where we're headed and talking about the various technologies that are available. So the reality, I think, for many crime scene units, ours included, is currently what is done by and large is dragging tape measures around a scene and making pencil sketches. So this is our workaday workflow for most scenes, is using tape measures, optical measure devices, and reference points or a reference line in the scene to then reference items of interest. And then we bring that hand sketch back, use basically a light CAD kind of software to make a diagrammatic representation of that scene. It is time intensive. It really only represents what things were measured at the time that the scene was processed. So there is almost by definition a loss of information there. Large scenes and complex scenes can be very time consuming. This often accounts for many hours on scene and many labor hours on scene trying to record a scene. So one of the things that we have been after, because like everybody else, we just don't have the resources to actually be able to do what everybody's expecting is done. Somehow we have to reduce the effort for our crime scene investigators on the scene, reduces their exposure at the scene to health and safety risks at the scene, but also how can we improve the completeness of the collection? Basically reduce what you could view as a version of bias, those things that are selected at the time of the scene to be measured and recorded, but also just those things that you cannot predict at the time you're processing a scene that may become important later. So very typical circumstance for us is this is kind of what a hand-drawn manual sketch is going to look like. Very diagrammatic, very cryptic, done at the scene at the time, in the rain, in the dark, in all of these various things that are less than ideal at the scene. But this is what I think probably the majority of crime scenes do. And like I say, this is very typical for what we are currently doing. That's then brought back. We're using a product called Scene PD, which is probably the dominant product that's out there for turning that kind of manual sketch into a more finished diagram. But you can see it's very diagrammatic. It's representative. It gets across the point, but it is a simplified version of what is at that scene. And you can also think in this issues of, I only have those measurements. And yes, while giving two measurements to two different reference points gives you an absolute positioning of that particular item within the scene, it is a complicated challenge of how I would actually calculate the time to the distance to something else. It's a trigonometric problem in there that's not straightforward to solve. So I think what, as I've been looking at this and as we have been evaluating technologies, you can see where the future really should be headed and is headed there rapidly. There are tools that are based around a process called photogrammetry, which is effectively using multiple images and reference points within those images to estimate where a given point is, both absolutely in space, absolute geopositioning of it, as well as the relative positioning of it. There are also technologies that have been around maybe a little bit longer that are based on LiDAR scanners or laser distance and ranging. That is the light, basically, version of sonar and radar. And one thing to stress right up here up front and all the way through, these technologies are evolving very rapidly right now. What has changed in the last 2 years has made photogrammetry possible where it wasn't even a couple of years ago. And all of these things are evolving very rapidly. We are kind of at a juncture here of logarithmic changes in the hardware as well as software capabilities. Where we're going to be at even a year from now is going to be a lot different than where we're at right now. And that's something really to take into consideration as you're looking at these things. One of the scanning technologies that I think probably more people are familiar with, we have two of these units that we've been using now for probably 3 or 4 years. There's two products that are LiDAR-based scanners, Faro and Leica are the two dominant products here. Like I say, this is basically uses an infrared laser to go out and measure specifically and directly the distance from the unit to a point. So it's a spinning prism there that reflects the laser out through the entire distance that it can reach, and it calculates the distance based on the return signal that comes back. So the time of flight that laser goes from the point of emission to the point of reflection. It is predominantly the industries that these products are developed for is survey and mapping and what's called BIM applications, building information management, where they're managing construction sites, changes over time in construction sites, things like that. So very large market for these things. I think really these were the first entry into the forensic mapping and crash scene reconstruction kind of things were these LiDAR technologies. So you've got from a fixed point, and it makes 360-degree scans in both X, Y, and Z from that fixed point. So you do need multiple scans to create the entire model. The Faro unit, our newer Faro unit, bats between 6 and 10 minutes, depending on conditions and what you've got particularly set up per scan. Our older one is probably more like 8 to 12 minutes per scan. So that can be time consuming if you've got multiple scans needed. You start a map of the area. So this one has 1, 2, 3, 4, 5, 6, 7, 8 scans total that were made in this. But as it's assembling and you process these data, it assembles what's called an orthomosaic view of the data. So it's the flat, basically top-down view of the data that you've processed there. Within those data, though, are these, you could think of them as stitched together 360-degree photos. So you get this photorealistic representation that you can pan around in 360 degrees through. This particular scene was in the dark, so that is in IR of the dark of it. It's one of the advantages of Faro, the ability to do this in the dark. It's also a disadvantage because you do lack a lot of the resolution and quality when you've got that. Here's a view from the more photorealistic representation, this stitched together 360-degree view. So you can click on each of the points that are in there where those scan points were, navigate between those, see the different view of the data from that point. Like I say, I think Faro has probably been and Leica are the two products that a lot of organizations use. They're good. They're just a little time consuming at the scene, and processing the data can have some challenges. I think what we are finding is in the last couple of years, changes in, one, the cost and availability of high power computing and storage, and also the rapid advancement in machine learning code and AI codes that allow for processing of data have made photogrammetric processing a lot more available. And I think it remains to be seen which of these technologies may advance faster, may become more field usable faster, and which of them may struggle to keep up. I don't know yet, but we purchased about 2 years ago a DJI Mavic 2 Pro. The DJI drones are probably at the moment kind of the workhorse drones that are out there. These little Mavics are widely used. They're pretty inexpensive. That drone plus some additional batteries and peripherals was about $2,000. We got a fairly high-powered laptop with a graphic processing unit in it to help run some of the software to process the data. Not sure I'd do that again, honestly, but for literally a few $1,000s, you can be in a circumstance to start processing some of this photogrammetric data to make models. We fly under a Part 107 authorization, so I've got FAA licensed drone operators that do the flying, and then we apply for authorization to fly through an app-based thing to fly that. There is what's also called a Part 91 authorization that is we're working on because of HFSC's kind of strange structure is not quite entirely government. It's taking us longer to work this out with the FAA, but probably most government agencies would probably work on flying under a Part 91 that gives you a little bit more flexibility. But there is rapid development in drone technologies that are available. And quite honestly, these little Mavics now, 2 years later, have been outstripped by far more functional drones at about the same price point. But basically what's going on in this is you think the photogrammetric processing is the idea that using two images, it's like your eyes. If I'm looking at it, I'm processing, I know where those two cameras are, if you think of your eyes as cameras, and I can trace a ray to a given point in there. And because where those two lines intersect, that gives me information about where that point is in space. So in this model, we've got two different images from where the drone flew over the scene. And if I pick the point of that knife as the particular reference point that I'm looking for, I can draw rays to that. So then the advantage in this is in processing this with the processing power that's available and the softwares that are now able to process the images and identify a wide number of reference points within those images. I mean, hundreds of thousands of points rapidly and with precision. I can now use many multiple rays. So I've got an array of about 130 images that the drone flew in a grid pattern over the scene. And it identifies that reference point in all of those images. And now I can get a highly accurate calculation of where that point is in space because I have identified it in more than 40 different points with 40 different angles. So you do that hundreds of thousands of times. Now you start to create a highly detailed and highly accurate model of that space that's there. Actually, everything that's down there on the ground is actually all modeled from data from this. This is just a graphical representation of what the software is doing. It can be highly scalable. One of the things we did as we've been working on validation was run this to see what kind of scale we could run at. We had a property out in Hill Country, Texas, where we ran this over and mapped 142 acres in about 42 minutes worth of mission time and had resolution on that of about an inch per pixel within the model. So we had resolution in the model down to an inch. So highly scalable. Obviously, if you had a 142 acre crime scene, that's a big crime scene, but you're really able to access stuff at a wide range of different scales. So this one actually is a actual scene here more recently as part of our validation, but being a little careful about not too many details of this one. I've got a few parts of it just to give you a sense of what we traditionally did. So, validating this in parallel of what we currently do with drone data. The diagram that we would have made or did make of the scene looks about like this. It gives you an idea where stuff is. But one of the things that I find particularly telling about this one is you've got the two reference points that were telephone poles there at the scene, and you've got the measurements to the cartridge casings from those two reference points. That's great, but it is a trigonometric problem, and actually I don't think you can truly calculate the distance of those cartridges to the decedent because the decedent's actually on a slope. And what's lost in this diagram is the angle and distance within that slope. So you don't actually know the elevation of that decedent relative to those casings. So basically what you can't accurately calculate from this diagram is the distance of the casings to the decedent, probably a relevant piece of information in that. And you can estimate it, and you can probably estimate it within a few inches. But if you were really trying to reconstruct a scene from this, that might be information that you would need, and you just can't get it because of the necessities of how we make these diagrams. That same scene with just the flight pattern of the drone. The flight pattern here had to be modified from more of a square because there was a big 90-foot billboard there that stuck up into the scene. So trying to fly the drone a little closer to the scene. But that grid, the drone was able to fly that grid in about 7 minutes and collected 130 images that made up ultimately the model that could be rendered out of that, which again, I'm not going to go into that model too much because it is an active investigation, but you can start to get the idea. 7 minutes on the scene with that drone. So even with setup time, everything else, you probably cut that scene processing time easily in half, if not some other fraction because you got all of that richness of information there in a 7-minute flight around that scene. I don't know what else to say in this. That's what these mapping technologies mean the difference of, whether it's Faro, whether it's drones, whether it's other thing. The ability to do it that quickly and that completely is just game changing. Now we are working and looking at a variety of other technologies. Obviously, a drone works great on a sunny, dry day outside, but what do you do inside? Yeah, there are some options, and there's getting to be some drones that offer being able to fly indoors. They're very small, so you don't get prop wash that messes things up. But ultimately, many crime scenes are in small areas. That idea of having a scanner that's at one point and looks around might actually be quite advantageous. We just recently started a pilot with a product called Matterport. You might be familiar with Matterport because if you have looked for a house recently, almost all virtual tours of houses are done in Matterport. So it has, again, a scanner unit that looks much like a Faro. It is not LiDAR based. It has organized IR beam as well as optical cameras. There's 6 optical cameras in it that sits on a tripod and turns just like Faro does, only its scan time is about 20 seconds per scan, and it constructs a similar kind of 3-dimensional model, point cloud, a mesh that's calculated over that, as well as the stitched together 360 kind of view of things from many multiple scans. So this is a facility that we have for training crime scene investigators. We call it the crime scene house. The house itself is about 2,000 square feet, and then the area around it was probably about another 2,000 square feet. So we mapped the entirety of the outside of the building and the interior of the buildings, about 4,000 square feet, in 100 scans. Took about an hour and a half. That's just a screenshot of the mesh of it. There's a screenshot of one of the interior shots, but I think all of these things are kind of tough to just show in static images. So shifting over to look at another advantage here is basically the ease of the user interfaces that are available with these. So this is the same model in the actual user interface. Blow that up there. So you can navigate through this and pan around. It also is supported in VR headsets, so Oculus Quest and Oculus Go. I think there's a few other headsets that it directly supports, but you can move between these, and it gives you a pretty good approximation of a fully rendered 3-dimensional representation of this. There is a point cloud and mesh behind this. So, and we've put measurement reference devices in here. So there's a vertical reference. Here's a long distance linear reference in the XY direction. And then we also have in here, these are GPS flags that get used in aerial photography. But behind this, because there is a mesh behind this, you can go in and add and measure basically any point to any point while you're in it. And that particular device is 16 inches on a side. So it comes out pretty much exactly like we'd expect it to. And you can navigate through this whole scene from inside to outside. It has tools within it that you can mark, like evidence items, navigate between evidence items, move between a 3-dimensional representation of the scene and those evidence items pretty seamlessly. So I can map over here to look at item 30, shell casing there, and the camera on this is about a 40 megapixel camera. So there's pretty good resolution of things that are imaged within this. So that's, like I say, this is one that appears to be a tool that could be quite advantageous for interior scenes. It does not work well currently in bright sunlight. That organized IR beam is very dependent on it. It is very dependent on that IR beam, and bright sunlight interferes with that IR beam. So there's that. There are a host of other tools that we're starting to look at because it is becoming parent, okay, I use, say, a Matterport tool interior, I use a drone outside. What can I do to try and provide an investigator one model that looks at all of that? Or are there ways that I can render this into a truly three-dimensional rendering of it so that if I put it in a VR headset, the parallax is maintained, all of the basically spatial representation of that is truly there in 3 dimensions that could be represented in a VR headset, not just this kind of semblance of a 3-dimensional view from these stitched 360 images. So there are some tools that we're finding are pretty helpful in this, in stitching together point clouds, because point clouds, which is this representation of the space, every point in there has an X, a Y, a Z coordinate, and a color, and then you've got a list of pretty close to 1 billion of those within a model. Cloud Compare, and there are a couple other tools, are tools that allow for taking these point clouds and stitching them together, comparing between point clouds. Another product called Sketchfab is useful in display mechanisms for the meshes. So the calculated polygonal representation that gets calculated between those points to give you a more photorealistic view of things. And then another product called Bentley Context Capture, which is a rendering engine for photogrammetry, along with Pix4D and Drone Deploy, are probably 3 of the major engines that are used out there for photogrammetry rendering. And out of that, you can get things like this. So this was drone data processed in Pix4D. This is the mesh view. That's just a screenshot of it there. And going into that so this is that same model in Sketchfab. So we processed the data that were collected from the drone. This is over the back part of that crime scene house. And I'm doing this because I'm headed towards stitching together all of these data that we've done over a crime scene house there. So that area back there is about 1,500 square feet. That data comes from a flight at about 35 feet over the area. This is all calculated and modeled from photogrammetry data. This is not photographic, but you can see it's pretty darn close to photorealistic in the modeling and the mesh that's there. There's a few places you can see some artifact, like in the door here, and obviously the overhang here. There was no data that the drone could get because of the angle, so that's absent there. But the rest of this is quite smooth. And this was probably mapped in 6 or 7 minutes is the drone flight time involved in this. But this is presented out of Sketchfab. Sketchfab also supports the VR rendering. So if you take this into VR mode, if you got like an Oculus or a VR headset, you can go into this and walk that scene to scale with the distance and things actually feeling like they're to scale, and be able to see accurately and to scale the spatial relationship of everything in there. So it is, you can see from the angle that the door, was blocked from this angle by the car, all of those things. It's actually an old minivan of mine that I've donated to the company for them to go do trajectory tests with and go shoot up the van. But all of that is quite easily rendered out of that. And this is kind of the advantage of like Sketchfab, is the ability to easily deliver to support a VR headset from the mesh. So one of the things I did want to give you a bit of a perspective on is the differences in the kind of data that you might get out of Faro versus Matterport versus drone. Faro, this is actually the point cloud from Faro data of a parking lot area just outside our lab. It was on a rainy day. So a couple of the things that you can see, one, the point cloud within Faro is quite dense, which is good. It's close to a photorealistic representation just as the point cloud. But Faro and that IR laser that it uses has real difficulty with reflective surfaces and water in particular. So this area of the pavement was all wet. So you can see there's basically absent data there because of the wet data. That in comparison to, this is actually the rendering of the same thing from Faro data, just a different angle looking at it. Again, you can see there's good representation of the crosswalks through there. You've got some absent data from reflective surfaces. You have some artifact in there from people that were standing around. This is one of the challenges that we have with Faro. Because those scan times are so long, you end up with more transient artifacts of people and vehicles standing there. It has less impact on your point cloud because of the faster scan times in Matterport, but you still have the same kind of issue. These kind of artifacts from somebody that was standing there and then ultimately moved before the scan was completed. This is the point cloud from the Matterport scanner used at the same time we were doing with Faro. We pulled it out of Matterport, processed it through Cloud Compare. So we had just the point cloud, and then we put that point cloud over in the Pix4D engine cloud as a means of displaying it. So you've got this nice user-friendly, easy, lightweight way of delivering the point cloud. But this is, you can see kind of the difference. The point cloud is not quite as dense, but things that are advantageous here are you have much less, you have much less reflective surface artifact. This area of pavement that was because of the difference in how the two products process things, you've actually got data there instead of reflective surface and absent data. Because of the rapid scan time, you can do a lot more scans, get a lot more complete rendering of the whole area here. You still have some of that artifact of people that were standing around. So there's a little bit here of people that were standing there, but it probably has less impact on the total calculation of spatial relationships if you've got too many people standing around in it. And just shorter scan time, there's less impact from people that may be moving through the scene that you just can't get out of the scene. But the point cloud is not as dense, which means a calculated mesh from it is probably not going to be quite as clean. And ultimately, your resolution of measurement is probably not going to get much better than about an inch, with reproducibility somewhere probably between about 2 inches to maybe 3 inches, depending on conditions. One other thing that I wanted to show, and there are, the capabilities, I can't stress enough how quickly all of this is changing. It just is really kind of difficult to keep up with how quickly all of the technologies are changing. And it is a real consideration of when do you actually try and step it to scale of some of these technologies. So I was trying to show a couple of different versions of the data that we had from the crime scene house, both out of Matterport and out of the drone. This actually is the two stitched together. So we took the point clouds out of both processing, drone captured, processed in Pix4D, Matterport captured, processed through Matterport, take the point cloud out of that, put those both in Cloud Compare, align those two point clouds in Cloud Compare. And then from that, we're able, so merging those two point clouds together gives us ultimately to deliver a representation of the entire 4,000 square feet, interior and exterior. And we just grabbed data from the drone that we captured just the back part of the crime scene house. We could have grabbed data that would have captured the rest of the crime scene house. It needs to have a roof and the rest of the crime scene house there from that drone data. But this stitched together then is an actual 3D rendering of areas where we couldn't get the drone. There's a lot of trees over this part of the scene, so you just can't get in there with the drone. But using Matterport through there, we're able to capture that accurately and really with pretty good fidelity, even in just the point cloud. So again, I keep saying this is just the point cloud. We've not calculated and are presenting a mesh there. We're still working on trying to figure out products that will let us calculate a mesh across all of this for a more photorealistic display of it. But within this, we've got all of the measurement possibilities. So we're still seeing measurement accuracies, even the Matterport data, accurate within about an inch of expected of those NIST traceable devices. And we can navigate this entire thing, both exterior as well as, and I'm not going to quite go through the door there, but I can go through the wall. And you can kind of see the aspect of the point clouds there as we're going through. And the point cloud actually having an accurate representation of even the thickness of the wall. So this is not drone data. This is point cloud from Matterport. But I can navigate through the building here, the entirety of the interior of the building. So you can see the traceability of these. That tape is actually 10 feet long, so we're accurate within about 3 inches of the actual traceable distance of that tape measured in this model. But it's getting very close to being able to pull off the shelf kinds of products to put together tools to make an entire representation of this. Now, end on one last product that we are just starting to look at, and it is actually a combination between a new generation drone, a product called Skydio, that's actually a company based out of Austin. It's one of the few drones that I found that is manufactured in the United States. And the photogrammetry engine that they used on this is the Bentley product. And this particular model is one of their demos. This isn't something that we've done, but it gives you a sense of what is possible even now and is coming rapidly. So this was captured with one drone. It's about a 40-minute mission time. It was 540 images that are behind this. And this has got to be one of the best meshes that I've seen in any of these products. It is really pretty phenomenal. And this is supported inside of VR headset. So if you go to this model in the VR headset, it is dizzying, the realism of it. But this is a completely three-dimensional, actually completely rendered model. And like I say, the drone autonomously flew to map this. And this is one of the products we're looking at of the possibilities that are out there. But it's got, from just the drone flight, it's got the interior of this cabin. And like I say, the mesh that is calculated with this is really pretty phenomenal. All of these technologies, whether it's Faro, whether it's photogrammetry, whether it's Pix4D or Drone Deploy or Bentley or Agasoft, they are rapidly evolving, and the capabilities that they have are really pretty phenomenal. So I think the only thing that we certainly are looking at of what's got to change is getting away from tape measure and a pencil to something like this. But I do think it is a real question mark in our heads of when do we step into these technologies at scale and commit to the investment for these technologies. They all have their strengths. The Matterport scanner is about $2,500 per each. Pix4D has a variety of different cameras that it can work with, from various drones to 360 cameras that range in costs from $300 to $15,000. So I think there is a lot of different ways to slice this. And I suspect what's going to be the case for the foreseeable future is all of these things are going to be tools in the toolbox. And it's going to take a few years to see if that stays the case. And you need, a Faro for a particular circumstance, and it may be better to use a 360 camera in another circumstance and a drone in another circumstance, or if 5 years from now all of this can be done with a couple of different kinds of drones. I don't know yet, but the capability of documenting a scene far faster, minutes rather than hours kind of faster, in a completeness that just you can't even comprehend as being possible in the diagrammatic methods that most of us are using right now, makes it really advantageous to try and figure out how to use this stuff. So I'll leave it there. I know that is a lot of different tools and a lot of different information, and happy to answer questions. So thank you.
All right. Thank you, Peter, for such a fantastic and informative presentation. Let's go ahead and get right into some questions from the audience. We've got quite a wide range of topics of these questions. First one I have here is, how would the accuracy of drone calculations be affected by adverse weather? Now, I know you talked about wet surfaces and like recent rain causing some issues because of the reflections there, but this question in particular is referring to more things, I think, disrupting the flight path of the drone itself, like adverse wind or something similar.
Yeah, can you hear me okay?
We can hear you great.
All right. Yes, adverse conditions for drones. One is dark, and two is wet conditions. That little Mavic 2 Pro is not rated for wet conditions. The way the motors are put together, it's very sensitive to moisture, so you really can't fly it in damp conditions. There are drones. Skydio has one. DJI has a couple of different models that are rated for flight in wet weather so that you could fly them in the wet. At night, it all matters about how you light the scene. And you certainly can light the scene. We've got a bunch of Fox Fury lights, which are great. They're portable, they're battery powered, they're kind of heavy to tote around, but they're quick to set up. They do a really good job of kind of neutral colored lighting of a scene, and you can use 3 or 4 of those and you can light most any scene sufficiently to be able to fly a drone over it and get pretty good resolution. We've flown that little DJI in winds up to 22 miles an hour, and it is remarkable how well it can maintain its path, its understanding of where it's at. And that really doesn't affect the measurement uncertainty or accuracy of the measurements. What does affect things is the balance between lighting conditions and how quickly the drone is flying. So in a lot of these photogrammetry softwares, whether it's Pix4D or Agasoft or there are a number of engines out there, but they all have various methods within their algorithms to try and control for what's called rolling shutter effect. And that is, as the drone is moving, you have a bend in the photos because the drone is moving at the time that it's capturing that image. Obviously, the darker it is, the farther the drone is going to move, and the time that it takes for the exposure time, the amount of time that it's allowed to hit that CCD plate, and the more rolling shutter effect you're going to have. So you kind of have to balance how quickly you fly the drone versus exposure time. Good news is the drones and the software really are pretty good at automating a lot of that. So that's not been the issue of really the conditions. It's more, can you get the drone into the area? I think is probably more the limitation of where we've seen drone is simply you've got overhanging trees, or you just can't get the drone physically in there to have enough of an angle on the scene to be able to take the photos.
Keeping with this overall topic of the drones, I've got another question related to the autonomous flying of the drones that you're using. And the main question is are all the drones that the Houston Forensic Science Center is using and testing, are they all flying autonomously, or is there some pilot intervention? What is that breakdown right now?
Okay, so how we have typically been doing it, it has been really convenient to use the drone with pilot control to basically help estimate the parameters that you want to fly in. You basically use the drone in a exploratory fashion to make sure that you're avoiding obstacles, that you're high enough up, what elevation you really want to set up the mission to run so that you're not running into wires or roofs or other houses. Oftentimes you can't quite tell from the application that you're looking at just what the extent of the range is. And so it's helpful to fly the drone around it and use it as that tool. Once you've got that idea, all of the drone deploy and Pix4D, which are really the 2 major products that you see used with drone applications, both of them in their applications for the capture of the data, they set up to run the drone autonomously through that mission. So you put basically a box or a polygon around the area that you want to fly. It establishes the grid or the double grid that you want to fly. And most of these, for you're trying to capture for 3-dimensional, it's a double grid that you fly in the pattern. And it calculates out how often it's going to take the pictures, what speed it's going to fly at. It will give you what's called the GSD, or the ground sampling distance, which is the distance per pixel that you're trying to aim at. All of that stuff is calculated in there. Once you get going, you hit start and it takes care of the rest of it. So like that 142 acre example, that took about 40 minutes. That took about 3 batteries. So it goes even so far as it will fly until it reaches the set limit on the battery, flies the drone back to you, lands, you put a new battery in it, hit start again, it flies back to where it left off and starts taking photos until it runs out of a battery again, come back, do the same thing over again. They are quite autonomous. The Skydio, that's kind of one of the things they're really making their market on, is the remarkably autonomous of those drones. It has even more pilot assist if you were even doing something that the pilot is trying to fly, and it is their product. I'm waiting on a demo of that one. I haven't seen it in person yet, but their product and what I've seen, kind of a video demonstrations of it, it flies in such a fashion that it will maintain a set distance away from a three-dimensional object and fly around it such that it captures much more data. That's what they used for that helicopter, and how you could get inside and the underside of that helicopter is flying that way. And it's a remarkable piece of artificial intelligence and sensors doing that. That is one of the things that at night it becomes more of a hazard, because many of the sensors that those drones use to do all that navigation are optical and dependent on light. So it can be more challenging at night.
I have actually a question here tied to those ground control points, and I think this is definitely deeper into utilizing drones for surveying type situations, very similar to what we're exploring here. But I do have this question, and this might get a little too deep into it, but do you have, or does the team at Houston Forensic Science Center have experience using post-processing kinematic or real-time kinematic drones instead of using a ground control point type drone?
Yeah, actually, I've spent a fair bit of time looking into RTK, PPK. RTK and PPK are surveying standards, and you think where drones' real market is. Forensics is this little tiny niche, basically, application for all this stuff. They're used in survey and inspection industries all over the place. And this whole idea of using ground control points, or the RTK, PPK, which are GPS technologies that allow for higher resolution, higher accuracy measurement of absolute geopositioning. Standard kind of retail version GPS is plus or minus about 6 feet. RTK, PPK can get you down to plus or minus about a centimeter in terms of its absolute geopositioning and reproducibility. So you can kind of go through this two ways. You can use, and all of the various softwares have mechanisms to use a ground control point, which is a fixed point on the ground in real time at the scene that you shoot a highly accurate measurement of, and use that to correct the model that's been calculated. Or you can have a drone that has RTK, PPK built into it, and therefore the drone's understanding of its position is much more accurate. Therefore, the model is much more accurate. What we've found is you probably RTK, PPK for the purposes of even scene reconstruction, or like crash scene reconstruction, is overkill. A drone that has RTK, PPK equipped, it probably adds $5,000 to $10,000 to the drone at least. And we've done some validation where we brought survey crews in to shoot highly accurate ground control points. So we have a fixed reference point in the model, and use that to compare data where we've corrected the ultimate 3D model using those ground control points and not. And with the drone, we find, yes, with the ground control point, you're accurate to within about 5 millimeters. Without those ground control point correction, you're accurate to within about an inch. So probably for the additional cost and certainly the additional headache, it's probably not worth it, at least in our hands and what we've seen. So an RTK drone, the other headache with it is the drone itself operates as the rover. Both RTK and PPK, you've got a fixed station that you connect to GPS satellites, and then you have a rover. Well, the communication between the rover and the fixed station can be blocked by trees, can be blocked by a lot of things. It can have difficulty with buildings around it, and it can be pretty finicky trying to get an RTK drone to fly accurately, depending on your ground conditions. And again, the level of additional accuracy that you're getting probably isn't worth it for most forensic scenes. That's been our experience with RTK PPK.
Awesome. Thank you. Shifting a little bit of focus now towards the other technologies that we talked about here. And specifically, I have a couple questions here about the Matterport scanner. Would a scan from a Matterport be the equivalent of a not to scale sketch?
Probably. The Matterport, and we are still playing with validating Matterport. And I saw one comment go through the chat there that they don't find Matterport as accurate, and that's what we're finding too. The point cloud is not as dense. The mesh that they calculate is their trade-off. All of these things are trade-offs in various risks and costs. They trade more ability to focus on the photorealistic imagery and the handling of that. The trade-off is their mesh calculation, and point cloud is not as dense and not as accurate and precise. We have been finding so far that Matterport is accurate, typically always within about 6 inches, and usually it's within about 1 to 3 inches at distances from 2 inches to 20 feet. So a Matterport scan really would be a two scale rendering, not a not to scale rendering. Same thing with what you're going to get out of Pix4D, Agasoft. There's another one that I'm thinking of. It's a Swiss company. I can't remember the name of the software. It'll come to me. It's one that's predominantly used in Europe as far as photogrammetry rendering software. What you see with Matterport is the relative within model accuracy and precision is pretty okay. Same thing with Pix4D, depending on the camera that you pick up. Something like Liz Q360, that's going to be pretty accurate within model, but its absolute geopositioning may be off by a fair bit. Been pretty impressed with the drones that we've looked at, that even the absolute geopositioning is remarkably accurate.
Shifting a little bit more into kind of the data generated and these images and whatnot, especially in relation to Matterport, who owns that data and how would that fit into the kind of evidence continuity and security of images as demanded by most courts, if not?
Yeah, and we have been scratching our heads some on this as well. So there again is a balance between, like what we've got, Faro and Liz Q360. They've both got a local viewer that works pretty well. The challenge is now when you're trying to share those data with somebody else, an investigator, a DA, and depending on where you've got to share that data, now you've got a local version of data and you need a local viewer to be able to see it. And what we've found, and this is one of the things we struggle with Faro, they're big data sets. So you got to burn them off onto an external drive, tote that external drive over to the investigator, give the investigator the external data as well as the viewer. They oftentimes have difficulty installing the viewer, using the viewer, getting it to work, admin privileges on their computer to be able to install it. And you've got this big data set that can be delicate. Pix4D, Matterport have a really nice, lightweight, web-based UI. You can control who has access to the data. The downside is neither one of them live in data architectures right now that are CGIS compliant. Matterport is in the process of standing something up in the AWS government cloud, which would be CGIS compliant. How we have looked at it and what we've kind of come down on is to look at the photos and the data that make up the model. That is basically the evidence, and the model itself is a derivative. So if the model were, so we take the images and we put those in our photo repository system with hash values, stuff like that. So it basically has an evidentiary protection over the images. And you look at all the rest of it as basically a derivative copy. So if the model were corrupted, questioned, whatever else, here you go. Here are those protected original images. Knock yourself out. You can build another model if you want, or we can rebuild the model and go from there. That's kind of how we're trying to split that difference of being able to have a really nice, lightweight, easy to use delivery mechanism that lets an investigator or an ADA or a defense attorney or anybody else that is appropriate go have full access and be able to use that model, move their way through it. They can even add measurements that they want without changing the underlying model. But then we've got a means of protecting the underlying data if, for whatever reason, somebody corrupts or has a question of the model itself.
Awesome. Actually, I have another question that just came up kind of related to that. Have you heard of or worked with a looks like a web-based application called Skybrowse?
Skybrowse, yep.
Uses drone video footage.
And it is, we were just starting to look into Skybrowse. It is what is referred to as videogrammetry. Some of the initial stuff I've seen from Skybrowse looks pretty impressive. One of the things that Skybrowse offers up as a real advantage for it is low light conditions, because you're basically flying the drone in video mode. So ultimately, best I can tell, it's actually still the same kind of photogrammetric algorithm behind it, because what you're doing with video is it's just that many more images. And honestly, some of these drones, like the Skydio drones, the camera on the Skydio 2 is a 45 megapixel camera on that Skydio 2, and the Skydio 2 is about a $3,000 drone. So the image resolution is getting pretty incredible. That probably affects more the ultimate model quality than anything else, is the image quality to begin with. So if you've got a drone with a 45 megapixel camera and low rolling shutter, good exposure, and it's not out of focus, your model's going to be remarkably accurate, remarkably precise in any of these products. But that's, yeah, Skybrowse is basically looking to overcome some of the rolling shutter artifact and low light conditions by using video rather than individual images.
Interesting. Well, we've got another question. I think this is a big one that a lot of people online right now, a lot of people watching, like to hear your thoughts on. What kind of methods are you using to establish the ground truth of the drones in the photogrammetric data sets?
It gets to be a tongue twister.
It really is.
Okay, so this is all kind of a validation question. We have been looking at all of these tools really as photogrammetric tools for measurement and treating them as a measurement tool. We are 17025 accredited for a crime scene unit, and it has been one of the ongoing conundrums for us with the crayon and tape measure method is you really can't give an uncertainty of measurement for any of those things in those hand-drawn diagrams. You've made that measurement once, you have no traceability of the measurement. You can't do an uncertainty. So I'm really looking to these photogrammetric tools as a means of actually being able to give an uncertainty of measurement on these things. So validation wise, we have gone through multiple mock scenes. I think we've done 4 mock scenes, and at each of those scenes we've done we've had a variety of tools that we've looked at. Some of the tools that we've looked at, we've dropped out because they just haven't really been sufficient. We've been narrowing down the tools that we've been using. So there's a couple other handheld tools that just really haven't been able to produce models that we've been happy with. So we've focused on the drone. We'll do the same thing with Matterport. On each of these mock scenes, do 10 to 20 individual mappings, independent mappings of them, typically by a different crime scene investigator doing the original mapping. So now we've got the inter-individual comparison, reprocessing some of those data within the software. So you have the within software variants. And then we have, you see, we've got those GCP flags in there. They're just a convenient high contrast device to put in the scene. And really what we've done with those devices is we've got NIST traceable measuring rulers that we've repeatedly measured those GCP flags. So we have an uncertainty of measurement around the GCP flag itself, and look at that as a NIST traceable ground truth device that we put in the data. So then repeated measurements of what we know to have a known distance with a known variance traceable back to a NIST device, and repeated measurements with that. So I've got a huge pile of thousands of data measurements that now we've got to crank through to calculate uncertainty of measurement for the model. Look at the uncertainty budget between measurement collection method, drone, software, device. Really, where all the variance lays is all of that stuff. The variance is tiny. The variance comes with the person who's looking at the software, making the measurement in the software. And so we've had multiple people make measurements of that device in the calculated model to have that layer of uncertainty in the uncertainty model. And what our intention is ultimately to say we've probably got an uncertainty budget for something calculated in Pix4D, and probably an uncertainty budget for something calculated in Matterport is kind of what it's looking like will come down to report out an uncertainty of measurement then for measurements that are made on those models. I'm trying to get through that because I know we're coming up on the end of timing there. That's actually a kind of a big question around this. The other thing that kind of ties into that in the validation stuff is, yes, there are machine learning components of these software. Largely what those are is for the identification of common features within images. And I've seen lots of different discussions about what does it mean to validate something with machine learning and AI, basically software and code that changes every time as it learns. The way we've come to look at it is really how you need to do it is the control that goes into every scene. So we've got validation that we try to establish the extent of operable conditions, and then every scene that's flown, a requirement on what control devices, something that's 2 inches, something that's about 2 feet, something that's about 10 feet, depending on the scale of the scene, that's in every scene. So now part of the data acceptance before reporting would be that your known measurement devices in the data have performed appropriately. And most recently, we've come down to figuring you can get NIST traceable tape measures for about $70. Is just stick the tape measure itself in there. Okay, fine. We buy a dozen NIST traceable tape measures. It's probably the easiest way to put something that is identifiable, particularly with Matterport. The image quality is good enough that you could stretch out a tape measure 2, 3, 4, 5, 6, 10 feet, whatever fits your scene. And then you've got a traceable device in the data that you can make multiple measurements on at multiple distances.
Awesome. Thank you. Well, we are out of time. I know we still have some more questions, but let me go ahead and let's throw your contact information on there for anybody that wants to try and follow up and see if you have an answer. And also just say thank you. We really appreciate it, Peter.
And yeah, please, any of those folks that are on there, I would be really interested in just kind of looking at some of the chat and the questions. It looks like there's a number of people that have kind of looked at some of these things. I am all over anybody else's experience. I know there's some folks that have been using this much more extensively, particularly in crash scene reconstruction. But these technologies are evolving so fast. It is pretty dizzying trying to keep up with it.
Absolutely. Absolutely. Well, again, always a pleasure. Thank you for doing this. And we appreciate your time.
Appreciate it.
Before you leave today's webinar, we ask if you could participate in a short 5-minute survey. You will see a checkbox icon directly above the chat. Simply click that button to be linked to the audience feedback survey for today's event. Your feedback about our webinars is critical information that helps us improve and continue to provide you the best webinar experience possible. If you could please take those few moments to complete the survey, we would greatly appreciate it. Lastly, across the top of the live stream window are links to all our social media profiles, including Twitter, LinkedIn, and Facebook, a link to our website at forensiccoe.org, and a link to listen to episodes of the FTCOE's podcast, Just Science. There's also a link to sign up for the FTCOE newsletter so you can stay up to date with everything that FTCOE is doing in support of the forensic community. Thank you again for attending, and we hope everyone has a great day.